Is that working?
Yeah, I think so. Okay, so everyone, we have Elliot Slaughter visiting today from Slack. He's going to be talking about the architecture of the Legion profiler. So with that, I'll turn it over to him.
Okay, so I figured I would start this by doing a short demo of what the profiler actually does because I'm not sure that everyone here is necessarily familiar with that. So we have some profiles hot off the presses from a run that I was doing. I'm going to start my activity monitor so I can track my memory usage here. I'm going to take a risk and load a big one. Okay, so this is kicking off the profiler, and I've got some runs that I did on a machine. This is a multi-node run, so I've got a bunch of different log files from different nodes, and it's basically streaming through these logs. It's going to be building a state, and we have. Yeah, this is my process here. You can see it uses a non-trivial amount of memory. This is actually real production data from an experiment I did, so that's part of why it's so big. Um, and what we should see here in a minute. So it finished parsing. Oh shoot, I'm running the wrong mode. It is spitting out. This is the old style profiler. The old style profiler spit out a file directory containing a bunch of things. So I'm going to kill that. There is a new profiler mode that I'm going to try to pop up here if I can. I'll just give this a minute to run. So, I mean, the way to think of sort of the overall architecture is we have a backend script that basically processes all the log files, and then in the old mode, it would spit out literally a directory that you could. That's what you could see it doing, up above the first time I ran this. And in the new mode, there are a couple of options. The one that we've sort of integrated so far is going to pop up in a UI here in a second. Here we go. So this is the profiler UI, and yeah, there's sort of what you've got here on the left-hand side. We've got controls. We've got the node processor selector here. And then we've got, these are utilizations, and this was for a production run, so of course I wanted my utilization to be very high. We've got not 100%, but it's pretty good on this run. And what you can basically look at is the different kinds of resources. So we have GPU, CPU, utility, I/O. This is some memories. System memory, zero copy. This is a different kind of memory, different GPU memory. And then we have, this is doing an I/O test. And so you can see the file memory. They all have different patterns. So you can see just sort of from glancing at the utilization, right, like the zero copy starts at nothing, it steps up. It's like clearly a step function here. The file memory, right, we go from 0 to like 100%, and then we sort of fall back down, right? We repeat that pattern. And so this is a little bit like if you're used to sort of standard profilers, it's a little bit different from what you might be used to seeing. So sort of the main interaction mode is you click to drag, and then I think I've got, yeah, right. So then you can use control keys to sort of flip through your previous zoom levels. So I'm going to zoom in here. We've got some tasks, and so when you're dragging, if you notice the top bar, it shows you, how much duration of the program am I looking at here. I'm looking at about 30 milliseconds, but some of these like really tiny tasks, like there's a little tiny thing down here, that part only, this last dark portion of this task was only running for 42 microseconds. So you can zoom through a whole bunch of different like orders of magnitude in the profiler. Yeah, but one of the things that's a little bit different here is that we track the states of tasks. So we have this task, this blue task. Let me zoom into this blue task. The majority of this time it is, this should be, there's something wrong with that. That should be waiting. The light blue color indicates that it's waiting or blocked. When it goes to sort of this medium blue, then it is ready, and then when it is fully dark blue, then it is running. And so you can look at things that maybe you don't care so much on the GPU, but then on the CPU, right, like this top level task spent just the bulk of its time waiting. So I can zoom out. Actually, the main task.
Is it okay to ask questions now? Or do you want to wait?
Yeah, go ahead.
The GPU line, is it GPU work on the GPU, or is this CPU submission to GPU work?
We're going to have to ask Mike that, but I believe it is.
It's the kernel's actually running on the GPU now.
So how do you track the pending, like the light blue versus the deep blue for that wait on the GPU?
Well, so actually, that's a good question. So I think we might actually be tracking both right now. So I know for certain that actually, it's going to depend a little bit on the backend profiler that Elliot's going to talk about. But I know that Legion records both the times on the host as well as the times on the device.
Right. So I was just wondering if that lighter blue is actually the launch latency of that kernel, essentially. And which means
no, I don't think that's the launch.
Which
latency.
means no.
Yeah.
Okay.
Yeah, if it was, it would be very long, right? So.
Wow, that's so curious. Okay. And then the average GPU is it GPU idle essentially, that or 1 minus GPU idle?
Right. This is utilization
because
utilization. I think
of the GPU. For example, there are many metrics. The GPU can be tricky, right? It's really that's what I'm saying is the GPU doing interesting work, or is it just busy, burning wattage?
Right. I don't think we're very sophisticated about that. I think right now, it counts it as used if anything is running at all, and I don't think we go
doing something.
Yeah, right. Doing something. Yes.
Yeah. Fair enough.
Right.
Yeah. Okay. Thank you. Do you have any networking as well, observability on the system?
So there are copies.
I know it's disk, right?
Right. Yeah. So if you go into Chan here, these are the channels. So if I scroll down, I should find some pretty big. Let me zoom out a little bit. Okay. Yeah. I mean, there's some these are disk copies. That is some fat list of instances here. Anyway, so there are disk copies here that are really, really gigantic. And then there are things, this should be, copies from frame buffer to frame buffer. So you can hover over this.
But you have inter-node communication, like networking.
Right. Yeah. So if you go node 0 to node 1, that's going across the network. Right?
Gotcha.
So if I zoom in here, then I can see,
Yeah.
These really tiny boxes.
The spikes.
Yeah. Right.
Yeah.
So then it'll tell you. I think this is not fully complete yet, but it'll tell you things like how much data, the instances involved, like how long it ran. We could compute a bandwidth, but we don't currently do that right now. So yeah, right. So you can see those things.
Yep. Great.
Right. So so awesome. as a user, right, typically what you're doing is you're coming to the top of this and you're saying hey, what's I'm spending all of my time on, right? And then you can basically drill down through these different things to see sort of what's going on. So I think that's it for demoing this. Are there any questions about this before I move on to sort of the code?
So is there any kind of Amdahl's law calculation on the data, or is that meaning critical path of what's?
We've we've had critical path in the past, and I don't have it set up for this profile, but we have the ability to do that. It is not necessarily super sophisticated.
Sure.
So I think it doesn't.
That's
too right.
Right.
You have to log a little bit of extra details to do the critical path analysis, which is a little more expensive logging.
Right. And in this version, we need actually the detailed SPI analysis to be able to do that. So it's even more expensive.
But the analysis, the critical path analysis is a offline task, or is this in the tool itself?
Right. Yeah. So the way
the experience like?
Yeah. So maybe I can talk about the architecture a little bit. So the way to think about this is there is essentially, it's not obvious because I've fused them into one piece right now, but there is a script which is intended to be run sort of as a processing script over all these logs. And in this mode, right, when you pass the view flag, it just pops up the UI at the end when it's done. But in the future, we're going to have like a serve flag, which would open a port, and you could connect like on a remote machine. Like I said, like this is using 16 gigs of memory. And so if there was an even larger profile than this, you'd need to find a bigger machine to view it on. And the server mode sort of gives you a way to do that. And we also are interested in having a mode to spit out like a static file that you can share. And so there is a separation between sort of like the backend component of this and the front end that you're seeing here, the UI. So the critical path and all that sort of like fancy business logic that exclusively goes into the backend. So I've got the code here. So if you're in the Legion repository, if you go under tools, there's sort of like a couple of things. So we've got sort of multiple generations of this profiler, and the old version used to be in Python. So that code is still sitting here. It still works. We test it, but it is obviously quite a bit slower. And so the new sort of fast version of the code sits up here in Legion Prof RS. RS is for Rust. So this is a Rust code base. And this is sort of the backend component of it. So there's sort of like two main pieces. This is the backend component. And then we've got another repository called Prof Viewer. And this is the front end component. So I think for most of the stuff that you need to do, you would probably need to know about the backend component. That's the main thing I'm going to go through. But I'll also, if I have time, I'll mention a little bit about the front end too. So if you know anything about Rust, it has sort of this canonical project structure, which is kind of nice. So Rust takes a little bit of getting used to if you're new to the language, but the advantage of it is if you've seen basically any Rust project ever, it is pretty much the same. So we've got sort of a project configuration here. I won't go through this now. And then we've got code in source. And basically, this sort of like main is sort of the driver for all this. And there's sort of like a couple of major pieces. So main sort of glues these pieces together. And if you read through main, sort of summarizing what we've got here, we've got essentially argument parsing for the first part of this. There's a bunch of flags. There's sort of grabbing the stuff out of the arguments. This is sort of like the core part there we deserialize all the logs. So you see that print message. When we saw this, right, that was the message we were seeing. So we deserialize all the logs, and then we build this state data structure. So we're basically going to make a giant state, shove all the stuff we parsed comes in here, and then we're processing all those logs. That's sort of, and then at that point you've got sort of your parse state, and then on the output side, then there's sort of one of a number of options. So you can sort of print some stuff, there's sort of a couple different formats that you can spit it out in, wherein this is the viewer that I'm running, but there's sort of a couple different ways that you can output the result of the logs. So I think for most of you, like I'll jump into the serializer here for a second here. You mostly don't need to know too much about this. The main thing you need to know is sort of this record struct. This is what Rust calls an enum. It's basically like a tagged union. So it can be one of, any of these sort of major things. And sort of the thing to know about this is basically copy and paste from Legion, with syntax changes. So these are all the things, somewhere in the Legion runtime, it will be logging these things, and then we sort of mirror the types over here, and then we've got parsing logic, which I think I will not go through. There are sort of ways to reduce the amount of parsing logic that you need to write in Rust. I have not taken advantage of that yet, But at some point, I'm planning to do that, and then 90% of the contents of this file will go away. So it's not really worth talking about the rest of this. But sort of the point is, when you're parsing one of these logs, what you get is basically a list of these statements, right? And it'll say, like here's a, partition, and then it's sort of like these are the IDs or the names, the various things. And so you get this sequence of logs coming out of the parser. Any questions about this? Okay, I'll move on. So I think in terms of like what most people would practically need to touch, the vast majority of it is in this state. And so this is basically this is the core data structure of the profiler, right? So if you think about the flow of the profiler, you start from raw log files, you parse the log files, and then you get those records. And your goal is to basically build this state. And there's a bunch of different stuff in here. One preliminary thing to mention up front is that if you're used to C++, sort of the number one difference with Rust is that this is not an object graph. So if sort of like the idiomatic way to build a profiler in C++ would be to say, like, I'm going to have, these 5 or 10 different kinds of objects, and then when you have one object refer to another object, you have a pointer to it or whatever, and you end up with this sort of ball of mutable object state that you're building in memory. And Rust is very different from that. So if you're coming from that world, you might be a little bit confused when you come into this code base for the first time. But sort of the way to think about it in Rust is that we're basically trying to build a database. So we're not going through and we're not, allocating, individual memory objects one at a time and hooking them up with pointers. We're basically trying to build tables, essentially. So they're relational, they're in memory, so there's no database backing any of this. But it has sort of the same sort of conceptual structure to it, right? You have data structures, so we're going to have like an actual state. State is an object. Let me find it here. So state is an object, and it's going to have a whole bunch of stuff, right? And so state owns all of these things. So we're going to literally, it's going to own processors, right? We shorten it to proc, but these are processors, these are memories, these are channels. So it owns sort of like those key data structures, and there's a bunch of different stuff in here. And then these things in turn, if I go look for the processor, then this is going to own what are called entries. So these are proc entries, so things like tasks. And so the state owns the processors own the entries, and everything is sort of built into this giant data structure, right? So one of the things that I did when I was building this version of the profiler was I abstracted a bunch of things that were sort of bespoke in the old compiler. And so when you get to a processor can have a bunch of different kinds of stuff in it. So if we go look for this proc entry, yep. Actually, we want kind, right? So proc entry, has some different kinds of things in it, but sort of one of the things that it has is this kind. Kind says what is the kind of thing that I'm sticking in here, and then this up here is the list of stuff that you can have, right? So it can be a task. Task is identified by some IDs, right? Each of these have their sort of identifying things that are sort of relevant. You'd have a task, a meta task that's like a runtime task, a mapper call, a runtime call, or a prof task. And these are, potentially extensible. If we were going to add, this is potentially, we could add different kinds of things depending on what it's basically trying to represent the data model of Legion, right? So whatever Legion executes, we need to be able to represent in here. But then all of these processor entries, sort of regardless of the type of this, they're all going to have certain common things. So they're all going to have a base. We can look at that in a second. They're all going to have, so then they can optionally have an op ID. So Rust has an option type. It can either be, if you're familiar with Haskell, it can either be filled with something or it can be none. It's sort of like a nullable type. And there's sort of a couple sort of optional fields here that you have to be a little bit careful about because they may not be there. So there's sort of a way to check that. It has a kind, it has a time range, so it like starts at this time and stops at this time, and then it has waiters, which are sort of the ranges that I was showing you before. So, a task waits at some point, then it gets put back on the ready queue, and then it starts running again, right? That goes in here. Yeah, so I think maybe we'll go look at base next. So almost everything that gets rendered in the timeline has a base. And so we have our own ID system in the profiler. So, Legion has IDs, of course, that is tracking various things. But if you think about like a task, like not everything necessarily gets a unique ID in Legion, or not all of those IDs are available to the profiler, and so we make up our own unique IDs. That's basically what this is. There's a little an allocator that we use when you create a base for basically fetch me a new ID, and then the other fields here are associated with sort of in the profiler when we had these stacks. Let me zoom in here. Right, when we're stacking these tasks, level is basically what level are you in this, in this stack of things. Okay, let me back up. Okay, so okay, so everything is going to have a base, and so that means sort of like some key things like the prof UIDs come along with that. Most of these things also have sort of time range and waiters. There's sort of like a couple of common things that most of these things have. One of the, I guess I'll sort of go into sort of Rust language stuff for a second. One of the things that you'll notice in Rust is, so this struct here has no methods. So it's unlike C++, you don't have methods sort of directly attached to structs, but then you have these separate impl blocks. So this is basically, think methods for this type. And so there's sort of some idioms there. New is sort of the constructor, so there's no notion of constructors in Rust, right? You just have functions that return some type, right? This is a function. It returns an instance of self, which is, proc entry, the type that we're implementing. It takes some things, and then this here, sort of type, curly brace, whatever, right? This is the syntax for creating an entry, an item, object of type proc entry. And when you see a name, just sort of a bare name like this is equivalent to base colon base. So like this is waiters is being assigned to something, other than, the name of the variable. In these other cases, we just, we pass them in with those names. So we just pass those straight through. So I think overall, so when you make these proc entries, we are going to be attaching them to the proc. They're going to live at the proc, and then we're going to basically have some indexes so that we can figure out where they live. So this prof UID is something we made up, right? The profile logs don't have prof UIDs in them. So when you're looking up a task, it gets assigned an op ID. And so if you want to look up, if the log refers to a task, it's always going to refer to it by its op ID, which means when you come in and you want to get a task, it's a two-step process. You have to get the task by its op ID, it tells you the prof UID to look it up, and then the prof UID gives you the proc entry. And so if you think about it, this is basically like the tasks here. This is basically like an index, right? If like this is one table essentially, right? Like prof UID is the primary key for this table, and if you want to look something up by op ID, then you have to look it up by, in this other index. But one of the things that is worth noting here is that if, not everything has sort of a unique key like tasks do. And that's one of the reasons why we picked this architecture, is because if you look at like these meta tasks, for example, first of all, the key is more complicated, right? It's op ID and this thing called a variant ID, sort of what kind of meta task it was. But then when this contains a list of prof UIDs, which means that this is not unique, right? There are multiple prof UIDs for a single like op ID variant ID combination. And so, sort of the key thing here is like prof UID is always unique. This other key, right, that we might have is not necessarily unique. So I think for the most part, you don't necessarily need to worry too much about that. So we've got an impl on proc, and that handles most of this sort of stuff, so you mostly don't need to worry about it. So like when you create a proc entry, for example, like you call this method and you pass in, what kind it is and the various things. And it mostly handles like all this logic about, tracking, all of the, what kind of operation it is and, how does it need to be indexed and like so on and so forth, right? Like it knows how to do that. Like it's doing all of this logic to do that. And it knows, for example, like if you're another kind, like we don't need to track it. We only track those two kinds. So like all of that sort of stuff, you mostly don't need to worry about. Like if you're interested in looking up a task, right, there's a find task method. So then if you're somewhere in the code and you need to get a task, then you say proc dot find task, and then it goes and it does that lookup, right? It's a two-step lookup, but you mostly don't need to worry about that. I think one sort of key thing in Rust is that it has strict mutability semantics. So if you're familiar with C++ and const, it is sort of like a souped up const, except in C++ you can get away with making everything non-const if you want to be lazy, and Rust really punishes you for that. So Rust is not going to let you get away with that. There are rules that make that really painful if you try to do that. And so one of the things about this to just notice here is that there are separate versions for the mutable and immutable version. So find task mute is the mutable version. It takes a mutable reference to self, and it returns a mutable reference to the entry. The immutable version takes an immutable reference to self, and it returns an immutable reference. Right, and there's sort of like the various, methods for different kinds of things. I think what I'll probably do at this point, I'll skip down to the parse where it's doing process records. So that is sort of like the state that we're building. When we get a set of log files, what we've got down here, there should be a method here. Yeah, so we've got this function, and basically what we're doing is we're running one record at a time. We're going to take, again, this is the mutable state. We're building the state. For some various reasons, we have some sort of side data structures here. That is a result of sort of a lack of certain ordering constraints in the profile logs. So there are some tricky invariants on the order that we get these calls in. And in some cases, we can rely on those orderings. In some cases, we cannot rely on those orderings. So for the cases that we can't do that, we have some data structures sitting over here that basically store those things, where we know that they may not come in the order that we'd necessarily like them to come in. So we don't, like when we have an instance, it lives in a certain memory, we don't necessarily see the memory that is associated with the instance before we see the instance itself. So we have a sort of a side data structure for that. But then inside of this method, what we've got is basically this match is sort of like a switch. So think switch, it's like a powerful version of switch. And we've got each of the types here, right? It's sort of, it's this or this or this or, whatever. And then basically what we've got here is the code to handle each of these kinds of things. And in most of the cases, we're going to grab some data structure on state. So this is, starting at state, we're going to get some data structure. Entry is sort of a clever way of saying, like, get me the thing if it exists, or if it does not exist, then we do this. The double bar here, that is a closure. So this is sort of the function to run if the thing does not exist, and what we're going to do is, execute that expression. And so most of the code has that sort of flavor, right? Like it's this kind of operation or this kind of operation or whatever. Let me see if I could call the create task. Right. Okay. So there, some of the things, this code base is, we try to use sort of just the right amount of abstraction. So if you only modify data structure in one place, there is not a reason, in my opinion, to go write accessor methods. If you create, a data structure in multiple places, or you have sort of complicated creation code, that's the sort of thing that we abstract. So in some of these cases, you could see, like I think up above, like I was just modifying some data structure. In other places, we've got sort of dedicated create methods. Okay, so here's sort of the create method for task. This is the logger record that we got from Legion for that task. And it comes with sort of a variety of stuff, right? The operator, the op ID, what task ID we're running, the variant of the task we're running, what processor it ran on, and then these are timestamps, right? So sort of the time it was created, the time it came ready, the time it started, and the time it stopped, right? So we got different timestamps. And sort of the main, so we create this time range object, right? Takes those timestamps, and that manages that, so we don't need to worry too much about it. And then we jump into this create task. So it's probably worth going into create task. And so this is basically responsible for managing all of those data structures in a way to keep them consistent, right? Because again, we're building sort of multiple data structures here. And so we need to do this in a consistent way, right? So this line here with tasks, this is the index of tasks, right? It tells you which, like if you come up with an op ID, you want to know what processor does it live on, then this is the data structure you consult to figure that out. So we update that data structure. And then sort of the pattern that all of these sort of create methods are going to follow is we have this allocator. This is the bump allocator for prof UIDs that we're going to take a mutable reference to. So that's the mutable reference operator. We're going to track that. And then we're going to get the processor. So this is like get me the processor. Again, like this is a mutable reference to it. Again, one of this unwrap here is basically everything in Rust is strict, right? So when you refer to something, like in C++, if you use the square bracket operator or the dot at, like it'll just let you do that. In Rust, it will force you to handle those errors. And so when, like, if this is some data structure, this is like a map, we're going to say, get me this processor, and it's going to return an option, right? So it might be there or it might not. Like there's no, like Rust has no idea. And so Rust is going to force you to do something. So you can either, like you could do a match here. You could say like, is this some whatever? Or you could do, in this case, we know that as a property on the ordering of the logs, we know the processor is going to come in first. And so it's safe to unwrap here. And so basically, I mean, the placement of the unwraps essentially encodes some of this business logic in the profiler where we know there are certain orderings on the logs that come in. And if we mess up, then this will panic. It'll throw an error and you'll get a crash on some line. So once we have the processor, then, this is the method that we saw before. And we basically pass in, the stuff that we saw, right? This is the base. It takes this allocator to get its prof UID, and then these are the various things that we're passing in. And so I think that is sort of like if you look at all of the other methods, they basically follow the same pattern. It's sort of that is the template for the pattern that we follow. And there are also, if you need to look up anything, there are usually sort of lookup methods. So find task, or the mutable version of find task. And so this knows, right, like we need to chain together several, like we need to look up this thing in tasks, get that processor, find that thing. And I think, one of the insights that we've had is like, even though we're doing sort of these chained lookups, it is actually better for overall performance to do that than it is to sort of build one of these giant object graphs. And one of the, maybe what I'll skip to at this point. So I'm going to stop looking at the sort of the main state construction. So if there are any questions on that part, it'd be good to get them now. Okay. So what I'm going to jump to now, sort of, I'm going to assume like we built all our state, and then there's sort of a couple of steps that happen after that. One of the steps that happens is this sort time range. And I'm just going to demo sort of why sort of having this separately owned state is useful. So this sort time range basically has, so we built all the processors, we built all the memories, we built all the channels, right? Those are sort of the 3 core data structures we built. And then for each of those, we need to go, and this sort time range is going to do some stuff to basically arrange the tasks in a way so that we're set up to build, sort of show the stacks of items that we had in the profiler. One of the really cool things about Rust is we have this parallel iterator, right? So if you're using standard Rust code, this would be just itermute. That would be like a sequential iterator. You could say itermute for each, whatever. You add par on the front, and suddenly this is a parallel iterator. And that is it. That is all you need to do. And the sort of the extra cool part is like this is actually safe, right? So it's not like unsafe C++ parallelism. Like this is actually safe parallelism. And if you try to do anything that would cause a data race or a deadlock or memory corruption or any of those classic parallelism violations, bugs that you can have, like that would be a compiler error. And it is sort of a very short edit. So like most of the stages, when I was running this, I wasn't talking about this, but like all of this file reading, all that happens in parallel. And so we can sort of maximize disk throughput that we get from the disk as we're reading data out. Like all of that log parsing happens in parallel. The building of the state, unfortunately, happens sequentially at the moment, though I've got some ideas for how we do that in parallel. But then this sorting time ranges at the bottom, like once we've built that state, this step happens in parallel, and then there's some other steps that we can do in parallel too. Okay, I think I will stop with the state at this point. And I will go over to the backends at this point. So this is sort of assuming, we've built the whole state. The state is there in memory. We did all the processing on it. At that point, usually what we're going to do is we're going to jump into one of a number of backends. And so what we've done is we've collected the different backends here, and there are several of these. Not all of equal sophistication. So sort of the classic backend that we've got is called Visualize. This is a backend that spits out basically a bunch of TSV files, so tab separated value files in a certain format, and then we have a JavaScript front end that reads it. So that was not what I was showing you earlier. That is sort of our legacy front end for the profiler. It has served us well, but it is also not terribly scalable. And so there's not too much, like you probably don't need to look into this too much. I am expecting most of our work going forward to go into sort of the new viewer. We also did sort of a brief exploration. If any of you are familiar with Chrome, Chrome has a built-in trace viewer used in the TensorFlow project, and we were doing an exploration in that, basically spitting out that file format. And there is a version, and it does work. It just turns out to be not as great as we were hoping for. So it has been our experience that like whenever we try to look for any of these existing tools to handle our profiling needs for us, we have been disappointed. So then our sort of the new viewer, the version that I was showing you at the beginning of this, lives in this viewer. Actually, I'll jump back up here for a second. This viewer file. One of the things that you'll notice is conceptually, like every Rust, if you think of a Rust library, is called a crate. A crate consists of multiple modules, so each of these files is a module, and then since we're in a directory, like a directory is itself a module that recursively contains modules, and so this mod.rs is sort of the file that contains sort of references all of the other modules in this directory. So the thing that I wanted to point out here is that this viewer is something that lives under a feature. So we can have, this is like an if-def. This is Rust's version of an if-def. So it's like saying if-def viewer, right? Then you include this. It's like a pound include here. This is saying like if we have configured this feature in this build, then you include this module. So I just mentioned that so that if you're building and you forget the feature, like when I ran, I guess I didn't show installing it. I'm going to jump up. Yeah, so when I built it before we started this, I enabled all features. This is a cargo install. Cargo is the build tool for Rust. I turned on all features. If you forget that and you are confused why it is giving you an error message that this view flag does not exist, that is why. But assuming you turn that on, then all of the sort of the code that is specific to this UI backend, that all lives in this viewer. Okay. I think that actually what I will do at this point is I'm going to jump over to the UI so I can talk about that for a second. So, and one of the cool things about this rewrite in Rust is that basically we were able to unify like a bunch of stuff that we had in separate technologies before. So it used to be we had a Python backend that basically spit out these files. We had a JavaScript front end, and they were both slow, right? That was not a great situation. So I rewrote the backend several years ago in Rust, and then just about 4 or 5 months ago, I rewrote the front end in Rust as well. And one of the cool things about that is that inside of this viewer file, it is importing Legion Prof viewer. That's sort of the UI. Takes an app, and then if you see this app code, like it calls app start, and it just kicks off the UI and it runs, right? So it is all like integrated, like it is one. It's a separate code base for the UI, but it's all built into one process. Okay.
When you switch back to the viewer, can you show us maybe some examples of what they might find in the viewer and how they might fix their code? Like how a user would actually use the profiler in the end to adjust their code appropriately? Improve their performance?
Yeah. We're kind of short on time. So what do you guys want?
Into your...
Yeah. I don't know that the UI, like I'm trying to think of what I would show in the UI. I don't know that. I mean, maybe what I could do is I'll try to walk through the code structure. So this UI, I mean, one of the things about this UI is it tries to be very generic. So if you go and read through the backend code, there's a lot of business logic. It needs to know very specific details about the Legion programming model and the exact way that it works so that it can correctly calculate all the things so that it can show them to you. This UI works in like pretty much exactly the opposite way. There is a generic data model, so this data.rs in the Prof viewer is basically the representation of the data. So everything that gets shown, like when I was up here, like everything that gets shown comes out of this data.rs. So maybe what I'll jump down to the bottom. So everything, so a trait in Rust is like an interface. So think interface in Java, abstract class in C++. Everything that you render in the profiler has to implement this data source. And then there are a bunch of sort of things that it provides. The key things that it has are this entry info. And so entry info is basically this data structure that represents think this panel over here, right? The panel that has all, actually I didn't show these this before. You can shrink all these things. When I expand a node, right, like these are all the GPUs and all these sorts of things. These are all entries in this entry info. And then for each entry, an entry is like a GPU. That's an entry, like this bar that shows you the stuff here, or one of these utilization plots, so like showing you the utilization for all the GPUs on a node. When you...
Yeah, I guess I can see all those utilizations, which is great. I'm just also trying to connect the dots in the end of who the end customer is you're trying to help, and or how they're going to go and interpret this to figure out how to refactor their code to get that benefit.
Well, they don't refactor their code. They change their mappers.
Well,
but that's
in some cases
code,
they do,
right? So that's great. But I just wanted to try to help to figure out how to connect the dots there.
Yeah, I don't have I wonder, did we have a recording? I did this at one point where I actually walked through a series of not like, this is a good profile because the utilization is pretty high. So like the first thing, like if someone shows me a profile, what I do is I scroll to the top and I look at utilization. And if it's like a GPU program, usually the GPU utilization is supposed to be high, or if it's a CPU program, then the CPU utilization should be high. And so that's just like the first like highest order bit. Like, are they doing something like halfway reasonable? So then sometimes when you get into these profiles, what you'll see is like GPU utilization will be low, right? So that's usually a bad thing. And then the question is why? So then there's sort of a couple of culprits. Like one of the classic ones is this utility line. If you see this at 100%, that is bad. That means the runtime is working very hard to do something. And sort of the classic easiest like first mistake that people make is they make tons and tons and tons and tons and tons of super tiny tasks. So like if I zoom into this, you might think those tasks are really small, but if you zoom over this, let's see here, this is 11 milliseconds here. This is 29 milliseconds here. This is 15 milliseconds. So it's actually pretty reasonable. I mean, there's some like super tiny things in here.
Yeah, that'd be
this is
big enough to cover the
quarter of a millisecond. But the point is, it has to be average performance, right? Like we don't care what, like there's some tiny little task that runs. That's fine, as long as sort of the average is high enough. So if you come into one of these profiles and like it's pegged at 100% of the utility, like that's sort of one of the key things to look for. The other thing, this profile actually, exhibits a pattern that would be potentially problematic in other cases. So you see this channel. This is sort of the aggregate of all of the data movement happening in the system. And so if you look at this profile and you don't know what's going on, you're going to say, whoa, like what is this, right? Like why is this at 100% for so long? But it turns out, like I have specifically, this happens to be from an experiment I did. If I scroll down here, it uses a disk. This is what I was showing. These are sort of the disk copies that I was doing in my program. And so I'm writing out a bunch of data to disk, right? Like it starts here, it stops here. And so that is basically corresponds to this bump where I'm, flooding the channel with all this stuff. That's because the disk write is slow, right? And this longest one, this is 10 seconds, which is pretty bad. But it's writing to a parallel file system, right? Like this is a 10 gigabyte file. I'm writing to a parallel file system, and that's just the performance that I get out of it. But the thing, the reason why it's okay in this case is you'll see this, there's this dip here in the GPU, but it comes back up and then I'm fine. So if I go, so one of the classic things that you would do in these profiles is you see like, okay, there's a dip. And this dip is not that big, but if the user had, so you might have a profile you like, it's fine, it's doing fine, and it comes out and there's huge dip. Imagine this being longer. It would be, if it were multiple seconds or something, that would be something you might want to investigate. And particularly what you can do, see the black line that comes vertically through this profile? That allows you to line up. So I can see that that start of that dip is lining up with this. So if it, in the previous version of this profile, it blocked for this IO to finish, which was horrible. And it basically meant that there was this drop to 0 because there was nothing to do until the disk IO finished. And then it came back up again. But we can zoom in here, right? So this is the structure of, this iteration. And you can see as we zoom in, there's actually more structure to that. It's not perfectly using the GPU. But anyway, if we look at sort of this falling edge right here, what you'll notice is the GPU actually overlaps this IO by a little bit, right? There's not a perfectly, like some of these profiles you come in and it is perfectly aligned, which means that something is triggering something else. But what you're seeing here is that actually this channel gets to start before the GPU's even finished. So even at this level, there's a little bit of overlap over here. But I think what I should be able to find here is right around the end of this. There should be, yeah, here we go. Right. So this is not the disk. This is 0 copy. This is copying frame buffer to 0 copy on the same node. So this is node 0, like that's the node. And then this is sort of the frame buffer. Every memory has a number. I think you can mostly ignore that because this is a one GPU system. But this is basically copying from frame buffer to 0 copy on this node. And what you'll notice is that we've kicked off a whole boatload of these copies. It's like, and pretty substantial. I mean, it should be about 10 gigabytes total, right? So it's like a gigabyte, almost a gigabyte, 100 megs. That's some smaller ones, but a whole bunch of, like, it's in aggregate, I think I measured it as 10 gigabytes of data that we're basically kicking off a copy. So the reason why, that gap is as big as it is because we're doing a copy of 10 gigabytes in that space. And so that's sort of, usually the utilizations will sort of clue you in to what to look at. And then what you typically do is you dive in and you basically ask, like, what's happening in that time period? Like, what lines up with that gap that I'm trying to investigate? What other things are happening on the system? So does that sort of explain it?
Yeah, thank you.
Okay, so I do actually have to go at 1 o'clock. But if there are any other questions, I am happy to answer them offline. You can find me on Zulip if you're on there, or if not, you could talk to Mike and he can forward you to me. So
I'll put anybody on Zulip who wants to talk to you.
Yep. Okay. Any other last questions? Okay, well, I think that's it for today then. Okay, I guess I'll stop the recording.